All right. So before I look at your answers, I want to actually point out a few things. Okay. So anyway, if you just look at this, you are given that this is the peg diagram that explains the solubility of these two substances. All right. Now you need to know how to explain this peg diagram. That's it. Okay. In case you haven't noticed, on your D2L, I know that some of you do because that's why some of you are not showing up these days because I'm posting all my videos on D2L, but you don't get the attendance points though, okay? Anyway, so section 6. So if you go to the announcement page, I've already posted all the lecture videos for Unit 3 already, okay? And then there are some videos from the Unit 2 Module 3 as well here and Module 4. So just after the mixing covalent compounds video, which was the Tuesday's lecture, I have the 6 spec diagrams video, okay? Here I go over all 6 spec diagrams in details, okay? So if you get a chance, and take a break from your Instagram, and then if you can watch this instead, and to make your notes, that would be really helpful. For an example, so if you go to, a second, okay, these are the possible peg diagrams. You can see that if you have a peg diagram like this, where the mixed state at a lower potential energy and a higher number of configurations, meaning both potential energy and the number of configurations favor the mixed state, it's going to be soluble at all temperatures. Okay, and then I also talk about the intermolecular forces and then how the temperature affect the solubility, because if you increase the temperature here, that's going to favor the state with higher potential energy. Therefore, it's going to decrease the solubility a little bit. And the other side of this coin is the mixed state being on this quadrant over here, this corner. At a certain point of time, I'm going to start calling this corner the naughty corner, by the way, okay, where you don't get any Christmas presents, okay? Anyway, so if your mixed state is in the naughty corner, then both potential energy and the number of configurations, mom and dad, okay, they don't, they hate you. Therefore, you are not favored at any temperature. You don't get a present, okay? So in other words, it's insoluble at all temperatures. And then I also talk about intermolecular force strength, because unmixed state has a lower potential energy. It should have the stronger intermolecular forces. And then also the effect of temperature. When you increase the temperature, it's going to favor the state with higher potential energy, meaning the solubility will slightly increase when you increase the temperature. Okay. So the peg diagram in this case was D, which is same as the spec diagram. So here's everything that you need to know about that. Okay. You don't have to memorize them. Make sure that you understand them. Watch this video, make a note, and try to understand them without trying to memorize it. And if you have any questions, ask. Okay. All right. Anyway, I have already closed this question. Let me see your responses. All right. We're going to get there. All right. I'm going to open this question again. But anyway, what questions, concerns, comments do we have? Any questions, concerns, comments? So one more time. The peg diagram given, in the peg diagram given, the mixed state is at a higher potential energy and a lower number of configurations, meaning both mom and dad hate mixed state. All right, both potential energy and number of configurations do not like the mixed state, meaning it is never favored. It is going to be insoluble at all temperatures. That's what it means. Okay. All right. Any questions, concerns, comments at this point? Anything? Okay. All right. If that is the case, I reopen the question. Oh, really? All right. The question must be reopened, but I'm getting something anyway. Is the question reopened or not? Is it open? I think there's something. Okay. Yeah. All right. That's fine. All right. So let's do another one. Oh, by the way, before I forget, while we're looking at the D2L, so on your D2L, on the exam material, I posted your front page for exam 3B. I hope it's just the front page, not the entire exam. All right. So when you do the review exams and also maybe like discussion worksheets and stuff like that, try using only the front page provided here. All right, see if you can answer the questions with the given information. If there's anything that is missing, okay, you need to make sure that you remember them. All right, so for example, here you are given the geometries, but it is, for an example, trigonoplanar. You can have either trigonoplanar molecular geometry or bent molecular geometry if you have electron geometry of trigonoplanar, right? But bent only happens when you have a lone pair. That information is not here. Okay, so you need to know that when you use this table. And also when it comes to four electron domain geometry is tetrahedral, but the molecular geometry can be tetrahedral if you don't have any lone pairs. It will be trigonal pyramidal if you have one lone pair. It will be bent just like in water if you have two lone pairs. So that information is given to you, but it's not complete. So you need to make sure that you understand that part. All right. All right. Do we have any questions, concerns, comments at this point? Anything? Your discussion worksheets are due next Wednesday. If you haven't started working on them, please start now this weekend, because at this point we are done with 96% of the material for exam 3B. So you can start reviewing. I think that should be enough of me talking, right? I know. All right, here we go. Here's the next question. No, this is not the next question. This is the next question. Here we go. This is me trying to re-emphasize the word generally. Right? You're going to see generally soluble, generally insoluble. What does generally mean? Okay. So that's the purpose of this activity. I think most of you are okay at this point. You know what generally soluble or generally insoluble means. Okay. I have more than 90% answers now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. So when you say generally insoluble, what does it mean? What does it mean? Anybody? Lux, what does it mean? Okay, but there's something else that we did with the number of configurations. All right. What does generally insoluble mean? Grace.
A mixture will have a lower number of configurations.
Thank you. The mixed state will have a lower number of configurations. That's what generally insoluble mean, right? Therefore, we can eliminate options A, B, and C right away. Why? In options A, B, and C, mixed state has a higher number of configurations, meaning they are generally soluble cases. Okay, so they are not relevant to this case. Okay, and then between D, E, and F, okay, in all of them, we have the mixed state at a lower number of configurations, meaning it's generally insoluble. But to decide between D, E, and F, we need more information, and you are given some information. It says that the solubility does not change when you change the temperature significantly, meaning the potential energy wise, both mixed state and the unmixed state has, what do you think? They should be similar. Yeah, exactly. All right. So therefore, only peg diagram goes with that is option E. Therefore, that's your correct answer. All right. I'll give you 30 seconds to think about this in your groups, and then I'll take any questions you might have. All right. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Right? Right. Anyway, any questions, concerns, comments? What questions do we have? Anything? You have a question, miss? Anything? No? Yeah? Yeah, yeah. So one more time, okay? Generally insoluble means the mixed state has a lower number of configurations. Okay, so options A, B, and C are out. Between D, E, and F, E is the only peg diagram with the mixed and the unmixed at the same potential energy level. Because you are told the temperature is not affecting the solubility, your mixed and the unmixed must have the same potential energy. Because if that was not the case, let's say that the potential energy is like in D, like mixed state has a higher potential energy. Then increase in the temperature must increase the solubility. If it was F, then increase in the temperature must decrease the solubility. But that is not the case according to the information given, right? Therefore, both mixed and the unmixed must have the same potential energy, and the only peg diagram that satisfies that is option E. Yeah? All right. Any other questions, concerns, comments? Okay. So if that is the case, so please play with these spec diagrams. I mean, watch that video. I mean, I'm going to go over, I'm going over all of them as well. The same thing over and over though. Okay. Pretty straightforward stuff. So at this point, we are done with Unit 3, Module 1 entirely, right? So what we can do is we are going to do the first half of Unit 3, Module 2 today. And I'm gonna leave a little bit to discuss on next Tuesday as well. But at this point, we are basically reviewing, to be honest. All right. Now, when it comes to Unit 3, Module 2, right? So it's really straightforward. The reason is we are not learning anything new here. What we do is we apply what we learned about intermolecular forces to larger molecules or macromolecules, or more technically, polymers here. Okay. Some example polymers are DNA molecules. These are natural polymers, or protein molecules like like myoglobin, hemoglobin, or rhodopsin, and other G protein coupled receptors and stuff like that. Okay, and then also they can be synthetic or polymers like nylon, right? That is used to make like dresses and stuff like that, and also polyethylene. I know that you have interacted with these polymers before. Okay, so what we're going to do is we're going to use our knowledge on intermolecular forces to explain the properties of this. And once we explain them successfully, we will even predict the properties. And at one point, we will actually come up with our own polymers with our desired properties. Okay, that's going to be the goals for Unit 3, Module 2. All right. Now, with that, so the hardest part of Unit 3, Module 2 is the first part. Why? We're going to understand what a polymer is, and then how to draw a polymer, especially the shorthand notation for the polymer, and also the monomers. That's it. All right. That's the hardest part. And the other part is pretty straightforward because we are just applying intermolecular forces. All right. So what I'm gonna do is I'm gonna use my notebook for a little bit here. Here we go. Okay. So I'm gonna draw a polymer now, and then I'm gonna show you how to get the shorthand notation for that polymer, and also the monomer for that polymer. Okay. Let me see if I can find my blue pen as well. Maybe not. That's okay. All right. So here's a polymer. All right. So goes on. Okay. Let's say that we have a chlorine sticking out from every other carbon like this. Okay. This is an example polymer. Okay. Obviously, I cannot draw the entire polymer because it is huge. As a result of that, I need to, say that it is going to continue by drawing dashed lines like that. Okay. It means that it's going to continue. Okay. So this is, the entire chain. But what we can notice here is in this polymer, 2 carbon atoms in the main chain are repeated over and over. Okay. So I'm going to pick this and this as my two carbon atoms, you can see that this is repeated over and over. Here's 1, 2, 3, and it goes on, right? This is repeated over and over. So what I'm going to do is I'm going to take out what is repeated, which is this 1 and 2 carbon atoms. Here's my 1, here's my 2. To the first carbon atom, we have a chlorine bonded. Okay. Then I'm going to draw a parenthesis around it, and I'm going to write subscript n. Okay. And this n is a whole number that can range from 10 to, I don't know, millions or something like that. It can be a large number. Okay. So it is repeated. And also, to show that this repeat unit is connected to other repeat units adjacent, I'm going to draw two bonds coming through the parentheses as well, like that. That's it. This is the shorthand notation for the polymer. This is my polymer shorthand notation. Okay. And the other thing you should be able to do, you will be tested on this as well, is to come up with the monomer for this polymer, because polymers are made by polymerizing monomers. So what monomer gave rise to this polymer? If somebody asks you that, this is all you need to do. You again write the repeat unit, draw the repeat unit. Okay, here's my carbon 1, carbon 2, and to carbon 1 I have, this chlorine bonded in this case. Okay, and instead of drawing parentheses and then drawing these two bonds coming out, you are going to draw an extra bond between carbon 1 and 2. That's it, done. This is your monomer. Okay, so your monomer always have an extra bond between carbon 1 and 2, okay, instead of like two bonds coming out to make bonds with the adjacent repeat units. All right, I'll give you a minute to think about this, and then I'll take your questions. Go ahead. Okay. Yeah, so have a double bond. I mean, an extra bond between those two carbons all the time when you have to come up with the monomer. Yeah. All right. So let me show you a few other examples of this. Now, here we go. So here's another polymer. This polymer is called polyethylene, right? And then this is the main chain of the polymer, and then this is the shorthand notation of polyethylene. This is the Lewis structure. I mean, I prefer line structures for this, but but you can draw the Lewis structures as well. And the monomer of the polyethylene has a double bond, an extra bond between these two carbons. That's it. All right. And does anybody have polyethylene today? No? Does anybody had polyethylene at a certain time in your life? Polyethylene? Nobody? I had a few hands. That's it. Okay. Yeah. I mean, anyway. So if you did not, if you never had polyethylene before, I recommend that you go to places like Fry's and Safeway, okay, and buy some grocery. Okay, why? When you buy grocery, they put your grocery in a bag, plastic bag. That plastic bag is made of polyethylene. So you will have yourself your own polyethylene that way. Yeah? All right. So that is polyethylene. I'm kind of surprised that you never had polyethylene before. All right. You should go shopping. It's fun sometimes. All right. Now, here's what I'm going to do. I'm going to do another example now. It's the same example I did in my notebook. In this case, get this, I am going to replace one of these hydrogens, not all of them, just one of these hydrogens with a chlorine atom. Okay, guess what? When you do that, I'm going to get another polymer called polyvinyl chlorine. Okay, this is also known as PVC. Now, where do we find PVC? Does anybody know? Does anybody have PVC at home? Yes, where do we have PVC at home? Thank you. In plumbing, right? In pipes, you have PVC. So the difference between the plastic bag and that pipe, the rigid pipe, is that chlorine. That's it. Okay. Now, any ideas why PVC is much, much stronger than, than polyethylene? Any ideas? Cole, what do you think? Why? I know Cole wants to talk. Cole, go ahead. Why is PVC stronger or rigid than polyethylene?
Is it because is it more flexible? Well, no, it's more rigid.
Like
Oh, well,
rigid, right? Because it's a pipe. I mean,
then well that it's because of the structure then, isn't it?
yeah, but why though? How do you explain this?
The bond angles? I don't know.
Okay, okay. I mean, we're getting there. Abby,
Is it because it has stronger intermolecular forces?
there you go. Thank you. Because it has stronger intermolecular forces between the polymer chains. Now, give me a second, Abby. What intermolecular forces? Why are the intermolecular forces stronger? Take the microphone, Abby. Why do you say stronger? Why would it become stronger just by replacing one hydrogen with chlorine?
I was thinking because chlorine has more protons than hydrogen, but yeah.
But why would it? So, what intermolecular forces will be stronger?
Oh, it'd be dipole.
Okay, so you made the polymer polar now, right? The polyethylene was a non-polar polymer. Okay, but when you replace hydrogen with chlorine, you made the polymer polar. Therefore, you're going to have dipole forces. Number one. What else? What else is making the intermolecular forces stronger in PVC?
Dispersion.
Shreya, can I have the microphone, Shreya, please? Maya? Shreya, what did you say?
Dispersion forces.
Thank you. Dispersion forces. Tell me more, though. Tell me more.
Because it has a bigger size and more electrons, it's gonna be more attracted.
There you go. Exactly, right? So hydrogen only had one electron. You replace that with chlorine where you have 17 electrons, right? You increase the number of electrons. You made the molecule larger. Therefore, it's more polarizable. More polarizable means you're going to have stronger dispersion forces. Yeah. Therefore, overall intermolecular forces are stronger. That's why PVC is stronger and more rigid compared to the polyethylene bag you're going to find at Safeway. Right? All right. What questions, concerns, comments do we have at this point? Anything? All right. So this is how we use our knowledge of intermolecular forces to explain the polymer properties. So this is like a preview. Okay. All right. So the other one is tetrafluoroethylene or Teflon. Okay. And where do you find Teflon? Does anybody have Teflon at home? Thank you. Non-stick pans, right? And also, sadly, they have seen that in newborn babies' blood, they have traces of Teflon. All right. So it's pretty common than you think. All right. Anyway, so these are just ideas of, the polymers that we interact with. Okay. Now, let's do one other thing. Now, I did this for you. I drew a polymer and then I drew the monomer of that. Now it's your turn. Here we go. Polypropylene is a polymer that is used to make plastic, what you call folders. Okay. Can you draw me the line structure of the monomer of this polymer? Go ahead. Yes, on your whiteboard. There are two ways of doing this. Oh, why do I? Anyway, right? So I mean, you know what? I mean, I'll show both ways. Okay. So this is all you have to do. Okay. You just need to pick any two carbon atoms from the chain, from the main chain. That's it. Okay. So here are your options. You can pick either these two. Okay. Because you can see it is repeated over and over. Okay. Or you can pick these two. Okay, you can see it is repeated over and over, right? So anything would work. Okay, so let me randomly pick any two carbon atoms. Okay, so I'm going to pick these two. Okay, so this part is repeated over and over, right? So if I draw the shorthand notation for the polymer, so that has two carbons, my main two carbons. Okay, let me call them 1 and 2. To the second carbon, I have a CH3 group bonded. Okay, and then you have these two hydrogens. Okay, bonded to these carbons. Okay, and then this is repeated over and over. So I'm going to call it n times. And then you should draw two bonds coming through the parentheses to show that it is going to be linked with nearby repeat units. That's it. This is your polymer shorthand notation, okay, or polymer structural formula. All right, but the question is not about the polymer structural formula. It's about the monomer. So when you draw the monomer, get rid of your bonds coming out. Just introduce a bond between the two carbon atoms in the chain. That's it, done, right? But they're asking for the line structure. In the line structure, carbon atoms are implied. So are the hydrogen bonded to carbon atoms. So I'm going to have, here's my carbon 1, carbon 2, and then the carbon 2, I have the CH3 group bonded. Let me call it carbon 3. Here's 1, 2, and 3. Between 1 and 2, I have a double bond. That's it. And that looks more like this option over here. So that should be my answer. Okay. Another way to do this is, I saw some of you did this. So I'm going to show what you did. Let me get rid of my doodling first. Okay. So you started by converting the Lewis structure given to you to a line structure. So you drew the line structure of the polymer. So you have CH3 groups sticking out from every other carbon like that. Okay. So you see that any two carbon atoms. Okay. So this is repeated over and over. Okay. So you take that out. This is what is repeated. You draw the repeat unit. Okay. Instead of drawing these two bonds coming through the parentheses, you're going to introduce a double bond or introduce another bond between them. Done. So this is my monomer. This is my polymer. That's the other way of doing the same thing. All right. What questions, concerns, comments do we have at this moment? Anything? I want to see your answers too. I want to see we did. All right. All right. So most of you selected this option. Okay. Now, not many of you introduced any other atoms like oxygen here, but yeah. So 84% got this answer. All right. Anyway, I'm going to reopen the question. But anyway, what questions, concerns, comments do we have at this point? Anything? Any questions, concerns, comments? So this is going from polymer to monomer. Now let's think backwards. Okay, let's go from monomer to polymer. All right. So I'm going to give you a monomer. Let me see. Okay. Actually, I'm going to give you the Lewis structure of the polymer to make things spicy. Right. All right. So we have CH3, CH2, CH. I'm thinking. It's not obvious, but I'm thinking. Okay. So I like this CH2. All right. So if I do this, we need to know that we need to have a double bond here, right? So CH3, this is CH3, CH2, CH double bond CH2. Okay. Now this is your monomer. Okay. Show me the polymer. All right. Whenever I ask this question, it reminds me of citrus peels. I don't know why. All right. I think we have more than 90% answers now. All right. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. Now, before I look at your answers, I'm going to do this myself. All right. So, first of all, you're given the chemical formula with the double bond and everything, right? So what I'm going to do is I'm going to convert that to a line structure because my options are in line structures. Okay. So when I do that, I would actually, label my carbons. I'm going to call this is my carbon 1, carbon 2, 3, and 4 because it's easier. You don't have to do it, but I mean, I find it easier to do it. Okay. So let me draw my carbon 1, 2, 3, and 4. Okay. Um, here's my carbon 1. Here's my carbon 1, carbon 2, and then you have a double bond between these two carbons. Okay. This is carbon 1 and carbon 2. And to carbon 2, I have the third carbon attached. Okay. So I have this carbon attached to it. And then to that, we have the fourth carbon attached. This is my 3 and 4. So this is still my monomer. This is not the polymer. Okay. This is still my monomer. Why? We still have the double bond. Okay. So now when I go from this to my polymer, I know what is going to happen is I'm going to still have my all the carbons, carbon 1, 2, 3, and 4, but this is going to be repeated n times over and over. So I'm going to draw parentheses and say this is going to be repeated n times. And then also I'm going to draw two bonds coming through the parentheses to show that they are bonded with the adjacent repeat units. This is it. Done. So this is my polymer. Yeah. And then I go back and check for this with my options, and I see that option B is the closest one to that. Okay, so I'm going to go with that. Option B is my answer. All right. All right. What questions, concerns, comments do we have at this point? Any questions, concerns, comments? All right. So I need some help. Lily, you seem bored, right? No, that's okay. That's okay. That's okay. No, I'm just kidding. Me too. I was kidding. Can I have your group just stand up for a second? It's not a punishment. I mean, they're helping us understand something. Okay. So, all right. Thank you for volunteering, by the way. I didn't force them at all. All right. All right. So come closer. I mean, not to me, to each other. All right. Sorry. All right. Now imagine. Now please pay attention for a second. Now, okay. Imagine these as my monomers. Okay. And then if you are monomers, you're going to have a double bond, right? So can you hold your hands like this? Like, okay. So these are my monomers with the double bonds. Okay. Now what is going to happen is, all right, you are going to break that double bond and make a connection with the person next to you. Can you do that? All right. Yeah. Hold hands. No, not both. Okay. You can hold hand. There you go. Yeah. You don't do that. Let's say it's not close. Okay. Can you spread out? Right. So this is my polymer. All right. Can you become monomers again? Monomers. Right. Break the bond and make connection. Polymer. One more time. Can we see the monomers? Monomers with the double bond. Polymer without the double bond. All right. Thank you so much. Right? Thank you. Yeah. So I know that you were wondering what the heck is this double bond is doing there, right? That double bond is important so that it can be broken to make connection with the adjacent people, adjacent repeat units. Okay. That's why we have a double bond in the monomer. All right. All right. Any other questions, concerns, comments? Any other questions? Okay. All right. So we are done with the hardest part for Unit 3, Module 2. Okay. Understanding polymers, how to draw the shorthand notation for the polymer, and also how to draw the monomer. And we're going from polymer to monomer and monomer to polymer. That's the newest part. Not the hardest, actually. That's the strangest or the newest concept we learn. And after that, it's all about intermolecular forces again. All right. All right. So with that, we are done with that part. Let's talk about properties. Okay. When we talk about the properties of the polymers, we are going to divvy up into two scales. The chain scale, that means the entire polymer, and then the monomer scale. Okay. What do I mean by the monomer scale? So in the monomer scale, I'll be looking at what we have at individual monomer level. For an example, in PVC, we have this chlorine that made all the difference. So that is looking at the monomer scale. Okay. In nylon, we have this oxygen and this nitrogen and hydrogen bonded to it. Okay. That makes a difference. In Teflon, you have these fluorines and so forth. Okay. And that is what is meant by looking at the monomer scale. Now, without talking too much, here's what I'm going to do. I'm going to give you a question because you already have this in you, right? Here are three polymers. Tell me which one of these polymers you expect to be soluble in water. Go ahead. Oh, yes. Okay. All right. All right. Here we go. Oh, look at that. Okay. Most of us, selected this as our answer. And then very few of us selected this. And then some of us say Teflon dissolves in water. Seriously? Your non-stick pans, okay? So imagine now, even now, you have Teflon in baby blood, right? Imagine this is going to be a soluble polymer. If Teflon was soluble, it's going to be it's going to be a disaster. All right. Teflon is not going to be dissolving in water. Okay. Because if you put some water on the Teflon, like non-stick pans, it's going to roll off, right? Okay. And actually, when you have like fluorine atoms bonded like this, they are really, very inactive, very inert. They're not going to react with anything. Not water, not your oil, not your food, or nothing. And that's why we're using that in non-stick pans. But right now, we are kind of, slowly, gravitating towards ceramic. I don't know, anyway, because of this problem. All right, anyway, no. So if you selected this, if you think Teflon is soluble in water, you should, get rid of all your non-stick pans, right away. All right. So, no. And then the polymer in the middle. Let me see. Okay. How many of you have this polymer at home? Anybody? Nobody has this polymer at home? Okay. So, I don't know. When I was an undergrad student, we had parties. When I go to parties, they serve juice in these, in cups made of this polymer. This polymer is called styrofoam. Maybe you have heard of that. All right. So styrofoam is used to make cups and plates. Why? It doesn't interact with water. Okay. Why doesn't it interact with water then? Anybody? How do we know that it doesn't interact with water, Sierra? Why wouldn't the middle polymer interact with water?
Because it's not polar.
Give me a second, Abby. I want to talk to Sierra for a second. Yeah? Sierra, what do you think? Thank you. Say that to the mic, please.
It's non-polar.
Thank you. It's non-polar, right? Non-polar material does not try to interact with polar material like water, right? So non-polar polymer will only have dispersion forces. Water has all three intermolecular forces. Therefore, water will, stick with themselves rather than talking to this polymer. That's why the polymer is not soluble in water. All right. The last polymer. Who has that polymer at home? Anybody? Does anybody have that polymer at home? Really? I don't know. I don't know. I use something called Tide Pods, where you have detergent, in a packet. Yeah? And that plastic bag is made of that polymer called polyvinyl alcohol. Okay? And then what happens to that? When you throw that in your washing machine together with your laundry, it gets dissolved. Yeah? Because you have, why does it dissolve in water? Anybody? You don't have Tide Pods? You don't use Tide Pods? Right? Exactly. All right. Now, why does that polymer dissolve in water? Go on, what do you think? What's the name? I'm sorry. David, can I have the microphone with David then?
Wait, why does the thing?
Give us it. David, go ahead.
Because it's not a hydrocarbon, so it's probably polar, and it also has hydrogen bonding as well, correct?
Thank you. It's a polar polymer, and that can talk really well with water, right? It's going to have small talks with water, right? So one, it is a polar polymer, right? It has a dipole moment in this group, and that dipole moment, the dipole can interact with the dipole of the water molecule, and then have dipole forces with water, like that. Okay, and also it can have hydrogen bonding interactions, right? So it has this hydrogen over here. That hydrogen can hydrogen bond with oxygen of water molecule, like that. Or you have this oxygen over here. Okay? This oxygen can hydrogen bond with hydrogen of water, because water has hydrogen covalently bonded to oxygen. So we can have hydrogen bonding interactions on top of dispersion forces. Yeah, and that's why polyvinyl alcohol, that polymer dissolves in water. All right, what questions, concerns, comments do we have? Anything? All right. So till then, you're going to be attending, I don't know. I had an example here that I cannot use anymore. But that's okay. Let's say that you're going to go on a humanitarian mission to somewhere like Ukraine or somewhere. Okay, I was gonna say like a campaign or something like that. Something anyway. So you wanna have a bulletproof vest. Okay, and then I'm gonna give you two options for polymers that you can use to make your bulletproof vest. All right, what would you use? Go ahead. To make your bulletproof vest, what would you use? So soon I'm going to open up a Dropbox for your one-page notes for exam 3B, and also a space for you to submit your exam 3B review. Okay, on top of the discussion. So you have plenty of review materials. All right, you don't have to search for more. Please don't do that. I have given you plenty of materials to work with. Okay, you have discussion worksheets, you have exam 3B reviews, and on top of that you have past quizzes and homework problems. All right, there should be plenty for you to review for the upcoming exam. Yeah. Oh, all right. So we already have 90% answers, let's say. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. All right. Three of us said that, I'd rather not wear a bulletproof vest. Okay. All right. Don't be brave here. Nobody's a hero here. Okay. Anyway, so we are between polymer A and polymer B. Here's the thing. If you want your vest to be made out of polymer A, you should go to an evening event like, I don't know, Apple Polishers or something like that, where you can, you enjoy it. So because polymer A is nylon. And what is nylon used for? To make evening gowns, like nice shiny things and stuff like that. Do not go anywhere near a war zone. Right? So please don't. Okay? So it's like C then, okay? So, but polymer B on the other hand is Kevlar. Okay, Kevlar is used to make bulletproof vests, bike tires, and stuff like that. Okay, now here's the real question. In one word, it doesn't have to be a chemistry word. Okay, it can be a food. Okay, can you tell me why why Kevlar is stronger than nylon? Go ahead. More time. So both nylon and Kevlar have hydrogen bonding capability, because in both nylon and Kevlar you have oxygen and nitrogen with hydrogen covalently bonded to it. Meaning So it's same thing with Kevlar, right? So we have nitrogen over here and hydrogen bonded to it, and then oxygen. Okay. So both of them have hydrogen bonding capability. Okay. But Kevlar is much, much, much more stronger. Why is that? I want to see your answer on your whiteboard. I don't want to see a whiteboard. I want to see the answer. Do you have a okay? Why is that? What's the word I'm looking for? Thank you. Thank you. Pancakes. Right? Pancakes. Tell me more. Eli, can you Maya, can I have the microphone with Eli, please? Thank you, Maya. Eli, what do you mean by pancakes?
They can stack, right?
Exactly.
Yeah.
Yeah. In Kevlar, you have these benzene rings which are flat, which are polar, right? What they can do is they can stack like pancakes, and that increases the surface area of contact. Therefore, all the intermolecular force strength goes up. Okay, whether it is dispersion, dipole, or hydrogen bonding, it's going to be all stronger in Kevlar compared to nylon because it's stackable, because of the planar geometry of these rings. All right. So let's do one for the road, okay? Just last one. Here we go. All right, I know that we need to leave. Okay, so I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Okay. So most of us picked the second polymer over here, and that's the correct answer as well. Okay. Why? You like interacts with like. All right. TS, can you go to the tables for still chatting and check with them? Thank you. All right. So, and then also you said that, I mean, we can achieve that goal by introducing more hydrogen bonding sites, and then you were stuck. I mean, that was the impression I got. So we got to that point, and then, we were not sure what to do at that point. Okay. But some of you did, but my feeling was that at least initially we got stuck at that point. You know what? I can actually modify. I'll do it here. All right. So here's what I would do. Let's see. This is my polymer. Okay. This is the initial polymer given to me. This is repeated n times. Here are the bonds coming out. Now what I'm going to do is I want to make it have stronger intermolecular forces to make it more sticky, right? So we can do that by introducing more hydrogen bonding sites. Okay, what do I mean by that? You can either do something like this. So you can introduce, say, something like an OH here. Okay, or it doesn't have to be an OH. Okay, it can be something else as well. It can be, let's say, an NH2. Okay. How do they introduce more hydrogen bonding sites? I introduce hydrogen covalently bonded to nitrogen, and that can have hydrogen bonding interactions, right? Or it can be, I don't know, I mean, not even here. I mean, we can actually use this part as well, right? So we can introduce hydrogen bonding sites over here. What about something like this? Okay, NH. Right? So as long as we are introducing like more hydrogen bonding sites like that, okay, yes, you're going to be strengthening the overall intermolecular forces. Why? You are introducing more hydrogen bonding interactions, hydrogen bonding contributions. Okay. All right. Other than that, we can also just make the polymer more polar, right? This will make the polymer more polar as well. Why? We have more electronegative atoms now, meaning we have partial negative charges. Therefore, it's going to be more polar. Or you can just make it more polar by introducing something like this. So this is my, okay, we can replace my CH3 group with the fluorine. Okay. So right now, I have made my polymer more polar by introducing more electronegative atoms. Okay, these are not hydrogen bonding sites per se. Okay, but this is going to make my polymer more polar. Okay, if I make my polymer more polar, it's going to have stronger dipole-dipole interactions. Therefore, we're going to have overall stronger intermolecular forces. Or you can forget about hydrogen bonding and dipole-dipole interactions and make the dispersion forces stronger. How can we do that? right? So we can do something like this, right? Here's my initial molecule. All right. So you can introduce something like a iodine or a bromine atom. Okay. Maybe I can introduce a bromine atom here. Okay. What did I do now? I replaced one of my hydrogens with bromine, which has about 34 more electrons. Is that right? Something like that. You can check the periodic table. I think the atomic number of bromine is 35. You can check that, okay? If that is the case, I introduced 34 more electrons and also bromine is larger. Therefore, this molecule is more polarizable, and as a result of that, it's going to have stronger dispersion forces, right? So you can have, like, you can modify the molecule in many different ways like that. All right. What questions, concerns, comments do we have? Anything? Anything, that still bugs you? If you get a question like this in an exam, okay, can we handle it? Yes, what's your name, sir?
Wyatt.
Wyatt, go ahead.
At the top of the molecule, we have an O negative to C, or an O bond to a C, to a carbon.
Uh-huh.
Can we and then introduce a hydrogen bonding site, or does that double bond have to stay with the molecule?
No, it doesn't have to. Okay, so again, just to repeat, if in case you haven't heard that, okay, Wyatt proposal is to get, take the molecule. Okay. Instead of having a double bond between this carbon and oxygen, all right, maybe we can make that something like this. Is it right, Wyatt?
Yeah.
Yeah, exactly. Yeah. So now what did we do? We introduced more hydrogen bonding sites, right? Initially, our molecule did not have hydrogen bonding sites because we did not have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. So by removing a single bond and making it an OH like this, okay, you introduce more hydrogen bonding sites. Therefore, you can expect that this to have stronger intermolecular forces. That is fine. Okay, and also, along those lines, you will most probably be asked to explain your modification as well, meaning explain how that modification strengthen the intermolecular forces, thereby make the polymer more sticky. So you can explain it. All right. So you can say that initially we did not have hydrogen bonding forces in our molecule, but by removing the CO double bond and making it an OH, I introduce hydrogen bonding capability. That's how we justify our answer. Yeah. That part is more important. I believe that part might carry more weight than actual modification itself. Okay. Anyway, so that's so that you know what you did. Any other questions, concerns, comments at this point? So what you need to pay attention to here is, all right, when you make this modification, you cannot forget the octet rule. All right. You cannot just randomly add or remove bonds and violate the octet rule. If that is the case, you will not get points for the modification. Okay. So what do I mean by that? I'll give another example. Instead of removing this carbon oxygen double bond, if you did this, let's say that you still have this double bonded oxygen, and then if you just put a hydrogen there, and then say we are fine, we introduce a hydrogen bond inside, okay? But this modification is wrong, okay? Because if you have a hydrogen like that attached to a double bonded oxygen, it cannot be a neutral element. It needs to be a positive charge. But you know that it's okay. But you know that this violated our, the octet rule, or at least the common bonding pattern. For that reason, this modification is incorrect. Okay, don't do things like that. That is one of the most common mistakes people tend to do during exams, violating the octet rule. Okay. All right. Any other questions, concerns, comments? All right. Oops. If that is the case, we'll do something else now. All right. So let's complete our discussion about polymer properties. All right. So far, we talked about the monomeric scale, like, how to change the properties of the polymer by changing, what we have in the monomer. Okay. Now, what I'm going to do now is to switch to the chain scale. We're looking at the entire chain. All right. And before, I think this is what I'm going to do. Without me talking about, the chain scale, I'm going to give you a question. And then based on that, we will have a discussion. Here we go. So here are three polymers. Actually, these are three common polymers, by the way. Okay. What I want you to do is I want you to tell me, answer these questions. Go ahead. Actually, there are like 5 questions here. Go ahead. I'll give you 5 minutes or maybe 3 minutes. There's a pattern here. Cool. You guys go. Okay. Hi, Robert. Like I'm worried about they have to do some work and they also have to write the final program so that they're fine.
And will they don't have, and they have to do the work with the note.
What is with the cleaner now? They have to do the post. Oh, what is the cleaner? It's not the cleaner.
And we're, so they're just doing the note and properly and making sure it works, that you know.
Again, if you want to talk to somebody, please raise your hand. We are happy to talk. And there are people walking around. We are happy to talk. Oh, fine. You need to look with the font.
Yeah, you can honestly, it's like, but it's not, it's fine.
I'm fine with it.
But I'm like,
That's the chain scale. We're not looking at, the atom molecule. We're talking about the chain. Then we have branching. That's the chain. I don't know. Get that out by yourself. But if it's a longer molecule, we want them yeah.
I think one of those questions is that you guys aren't supposed to know it right now.
Yeah.
You haven't done anything about this yet. So I feel like let's hear what's it's like. Let's give him a couple minutes to hear what he says. Because there's a couple different ways to think about it. And I mean, you can think about the way it's stacked, or you think about the way it's makes. A lot of different.
We'll lose the glue properties, but we were not worried about it.
What is
Okay.
the difference if you were to do it with like a word?
like, I doubt she.
I'll tell you I'll figure it out.
Yeah.
I'll tell you what works with it.
All right, we are getting there. I think we have close to 80% answers. How are we doing over here? So branching, what it is? What is the branching there? It increases the surface area of contact or
Yes, it does.
Can you go back and check your notes one more time? When I say branching, I mean, I talk about my grandmother's umbrellas. I know my grandmother used umbrella to, reduce the contact, not increase the contact. So can you check one more time? But not the notes. Maybe we should have in our about something about branching.
It was wait.
Can I say it?
I don't think I have. We're about to do that right now.
I don't think you're ready to ask for the branching.
Really?
I don't think he was.
Oh,
We talked about like
Okay.
that's something.
It's not like plain. It's a plain atom. Maybe like a cell,
I think.
I didn't hear the last part. I'm sorry. I mean, I'll come back. I want to hear it though. How you guys doing here? Okay. Yeah.
So if it's the less branching, the higher the overall tenor is, right? Typically.
Yeah. Stronger than
So the smaller branch, the longer branch, right?
There are no branching.
Or not branch, sorry, but like. Longer, because we have a higher density.
Absolutely.
Okay.
All right. So we have more than 90% answers now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. I didn't check this side of the room next time. Okay. All right. So here are our responses. Look at that. Okay. So most of us said, some of us selected B. Anyway, that's fine. Okay. Most of us said highest density would be polymer A. Where's polymer A again? Yeah, polymer A. And highest rigidity. Okay, almost, yeah, again, polymer A. Anyway, it is like the votes. Anyway. And then highest strength, polymer A. Highest viscosity, polymer A. And highest melting point, polymer A. And that's the correct answer as well. Why? Why? William, okay, and give me a second, William. Can I have the microphone with William, please? Oh, you want here? Okay. William. All right, William, tell me more.
Molecule A has the strongest intermolecular forces because it can get close to each other. It's flat like a pancake. C is like a football. It can't
Okay.
get close to each other.
Oh, thank you, William. But okay, so I agree partially with you. All right. So I agree that polymer A has the strongest intermolecular forces compared to B. Okay, because it's longer, meaning more polarizable because you have more electrons. Okay, therefore it's going to have stronger dispersion forces. All right, strong intermolecular forces compared to B. All right, and then it's going to have stronger intermolecular forces than polymer C as well. Why? C has branching. Branching, okay, when I talk about branching, whenever I discuss branching, the thing that comes to my mind is my grandma's umbrellas. Okay, she used those umbrellas to reduce the contact between her and the people near her. Right? So the same thing goes with this branching in this molecule as well. Those branching reduces the surface area of contact. If the surface area of contact is less, the intermolecular force strength is going to be weaker. Okay, that's why A has stronger intermolecular forces than C. Now, William, the thing I did not agree with you there was the pancake part. None of these carbon atoms are trigonoplanar. None of them are planar. They are tetrahedral carbon atoms. 3D is going to be like all over the place. Okay, because it's a 3D atoms. All of these are 3D atoms. Okay, if you want to talk about pancakes, these don't remind me of pancakes. Why? We do not have any trigonal planar carbon atoms here. Does it make sense, William? Yeah, we only talk about pancakes when we talk about like the benzene rings, so phenyl rings where we have trigonal planar carbon atoms. Yeah, but other than that, I mean, I like that answer. All right, what questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Let's see. All right. If that is the case, so this is what is meant by using the chain scale. All right, we are not looking at individual atoms in the monomer. We are looking at how long the chain is, okay, or whether the chain has branching coming out or not to decide their properties. Okay, so branching reduces the surface area of contact, thereby weakening the intermolecular forces. Okay, and also the shorter chains have weaker intermolecular forces compared to longer chains. Right, and the other thing is, just like stronger the intermolecular forces, higher the boiling point, melting point, viscosity, density. All right, when it comes to polymers, strong intermolecular forces means higher density, higher rigidity, higher strength, higher viscosity, higher melting point, and so forth. Okay, it's the same trend. Yeah, Kimberly. Yes, can I have the microphone there, please, Rana? Kimberly, raise your hand. Oh yeah, there you go.
So is that the case for like every single molecule in a way? So if it has higher IMF, it has all of them?
Exactly. Stronger the intermolecular forces, higher the density, higher the rigidity, higher the strength, higher the viscosity, higher the melting point, but lower flexibility.
Or flexibility.
Yeah,
Okay.
that's what I would say.
Thank you.
Yeah. Any other questions, concerns, comments? Okay, so there's one other thing that we need to discuss in Unit 3, Module 2, but I do not think that's on your test, but that's okay. But this is going to be on your review though, okay? So that is cross-linking. Okay, so what we are doing in cross-linking is, I feel like I should use my notebook rather than this. All right, so what is meant by cross-linking? So let's say that we have, I'm going to zoom out. Okay, here's a polymer chains without cross-linking. I'm going to call this P. All right, cross-linking means you are connecting the polymer chains to each other, sometimes via covalent bonds, or sometimes via intermolecular forces, like what strong intermolecular forces. Okay, usually there are actual covalent linkage between the polymers. Okay, I'm going to call this CP for cross-linked polymer. So this is my polymer, this is cross-linked polymer. Okay, now here are two questions for you. Where do we have stronger intermolecular forces, stronger interactions, in the polymer or in the cross-linked polymer? Okay, can you write your answer on the whiteboard, everybody? Right? Where do we have strong intermolecular forces? And also they are for lower potential energy. I want to see your answer on the whiteboard. You have a 50% chance of getting this right. There's only two options, P or CP. Thank you. All right. Now, can I'll give you 10 more seconds, everybody. I think some of us are getting the whiteboards. Thank you. Wonderful. Can I see the whiteboards, everybody, please? Thank you. I see CP, 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 CP. I don't think there's any votes for anybody else. All right. It's CP all the way. All right. So cross-linked has stronger intermolecular forces. Why? Because of these constraints, they are forced to stick together. Okay. As a result of that, they are going to have stronger intermolecular forces. Okay. We know stronger the intermolecular forces, potential energy must be higher or lower. Thank you. The lower the potential energy. Okay. So the potential energy wise, CP must have a lower potential energy than the polymer. And what's the other part that I'm going to talk about next? If I talk about potential energy, I'm going to talk about, thank you, number of configurations next. Okay. On your whiteboard, where do we have a higher number of configurations in P or CP? Go ahead. Higher number of configurations. Second, 10 seconds. Can I have your answer on the whiteboard too? All right. I want to see your answers in, okay. Can I see whiteboards now, please, everybody? We have a higher number of configurations in, thank you. What about this side? I only have one, two. Okay, thank you. Yeah, it's the polymer, right? He has a higher number of configurations. Why this is the case? When you have links between the polymers, when the polymers are forced to link together, you're going to have less freedom, meaning less ways of arrangements. Okay. As a result of that, you're going to have a lower number of configurations in CP compared to CP compared to P. All right, this is it. I think when it comes to cross-linking, this is the main thing. You know, you're going to put this in a diagram in a second. And the other thing is I want to point out that, you know, a common area, a common field where cross-linking is used is the rubber industry. Okay. So if we didn't take the natural rubber is not that strong. Okay. So, I mean, they're not making tires out of natural rubber because they're going to wear off very easily. All right. So what they do is they cross-link the polymer chains of the natural rubber using sulfur. We call this vulcanizing rubber. Okay, and make vulcanized rubber. Vulcanized rubber is the cross-link rubber, and that is much stronger, and that can be used to prepare your tires and stuff like that. Okay, because it is much stronger than the natural rubber. All right, keeping that in mind, here's a question for you. Thinking about vulcanized rubber and unvulcanized rubber. UV stands for unvulcanized, meaning no cross-links. V stands for vulcanized, meaning you have cross-links.
Longer interact.
All right, we have more than 80% answers now. Close to 90%. All right, we have more than 90% answers. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right, and here are our responses. Oh, look at that, that's beautiful. And that's the correct answer as well. All right, any questions, concerns, comments at this point? We are done with Unit 3, Module 2. All right. Anything? Any questions, concerns, comments? So there's another part in Unit 3, Module 2 where we talk about polypeptide chains, okay, which is, you know, basically protein molecules. Proteins are made of amino acids. Amino acids are the monomers. They polymerize to give you the polypeptide chain, which is what you find in in protein polymers, okay? But you're not going to we are not going to discuss it today in Chem 151. You're not going to see this on the exam as well. But there are some questions in the discussion worksheets about that. So, you know, yeah. But anyway, I mean, it's not talking about anything else. It's not about the polymer. It's about, you know, whether you expect the chain to be bent a certain way or the other. That's it. All right. The idea is the amino acid side chains have, some of the side chains are polar If it is polar, they like to be exposed to water. Some side chains are non-polar. If they are non-polar, they like to hide from the water. They are hydrophilic, okay, hydrophobic. Okay, so they're going to hide away from the water molecule. As a result of that, when the amino acid polypeptide chain folds, it folds in a certain way where the hydrophobic residues are hidden from the water and the hydrophilic residues, the polar residues, are exposed to water. All right, I discussed this during my office hours as well. I mean, I thought of mentioning that, but you're not going to see that on your test or quizzes or anything like that. But maybe you might see something on your discussion worksheet. So, all right. Any other questions, concerns, comments at this point? Okay. So if that is the case, this is what I want to do. I want you to go to Unit 3, Module 2 homework for a second. All right. Let's do this. Let's tackle a few of these homework questions, okay? Because I really want all of you to do at least complete at least one attempt of this homework before before Friday's exam. All right, let's try this. Unit 3, Module 2. The first question. Here we go. You might have a different version, but the idea is the same. Can I increase the size somehow? Have a different question? Okay. Same idea. We can try it. Let's do the question on your screen. You can do it, yeah? So if you have a different question on your homework assignment, do yours, okay? Because the idea is the same. And then if you have more time, do the one on the screen as well. So that, I mean, we can save some time as well, right? We do that. Yeah. But I want you to try the problems before looking at it. Yeah.
Right out.
Get same question? You guys got same question. Okay. Okay. What did you tell me? You did already?
Yeah.
Oh, okay.
But remember, this one has a bond.
All right. All right. So I only have 31 responses yet, but that's okay. I guess. I think you at least try this on your whiteboards. Okay. So no, I mean, I'll show the way I would think about this. Okay. I mean, I hope that I make a mistake and you catch. I mean, you can catch that mistake and point that out. Okay, that's going to be the goal. All right. Now, first things first. If this is my monomer, when the monomer becomes the polymer, this double bond has to go away. Okay. If you can remember, the monomers have a double bond, like like this. That double bond needs to break to make the connection with the adjacent monomers. All right. So that needs to break. For that reason, I know that it cannot be options A or D. Okay. And then I know in my polymer, in my monomer, I have 1, 2, 3 carbon atoms, and the fourth one, nitrogen is attached to the third one. Okay. And then 1, 2 is always what is repeated. So this is my 1, 2, 1, 2. Okay. To the second carbon, I need a third carbon attached. In option B, I don't have that. Therefore, that is out. And that's going to leave me with option C as the answer. So option C should be the answer. That's it. All right. What questions, concerns, comments do we have at this moment? Anything? Okay. So if that is the case, let's do another one. All right. This time I'm giving you the polymer and I want you to show me the monomer. Go ahead.
I'm doing okay.
All right. All right. I think some of you have already submitted the answers as well. How are we doing today? Wonderful. Wonderful. All right. So now again, so when I walk around, okay, so some of the questions, I'm hearing, I'm not getting them directly. I'm hearing, where does the double bond go and, stuff like that. Okay. Here's the way I tackle this. Okay. Look at this now. Now, remember in our polymer, always 2 carbon atoms are repeated. Ritika? Huh? Give me a second, okay? Yeah, 2 carbon atoms are repeated all the time. Okay. Therefore, I'm gonna actually mark them. So here are the 2 carbon atoms, 1 and 2 carbon atoms that are repeated. Okay. And then where does the double bond go? Between those 2 carbon atoms. That's it. Okay. Now, here's my 1, here's my 2, and there should be a third carbon, and to the third carbon, a fluorine should be attached. Okay. So if you think about this, so this should be my 1 and 2. Here's the third carbon. On top of a fluorine, there's another group attached here. Therefore, that is out. Okay, that's just one fluorine atom attached to the third carbon. Okay. In option B, here's my 1, here's my 2. Okay. And then here's my third one. And to the third, I have a fluorine attached. This seems really good. Okay. In option C, here's my 1, here's my 2. I have 2 less carbons here. Therefore, C is out. In option D, here's my 1, here's my 2. There's no third carbon here. Right? There's a fluorine, and fluorine can only form 1 bond. So this is incorrect. Okay. Therefore, the correct answer is option B. Done. Huh? All right. What questions, concerns, comments do we have? Anything? Any questions, concerns, comments? We have a question over there. Remember your name, miss. I'm sorry. What? Jacob, can you get the question now? Yeah, you can. Yeah. All right. So let's do another one. Here we go.